November 14th, 1969. Cape Kennedy, Florida. It is raining. Not a drizzle, real rain. The kind of gray, cold, low-ceiling morning where you look up and think, maybe not today. A cold front is sitting right on top of the Space Center. The clouds are thick at about 10,000 feet, and the wind up high is screaming. The President of the United States is standing out there in the weather to watch, and 3 guys are strapped into a tin can on top of 3,000 tons of kerosene and liquid oxygen, and somebody down in the control room says, "Go." That is how the second moon landing almost became the shortest mission in the history of spaceflight. Not because of a broken engine, not because of a computer error, because of electricity. And I mean the kind of electricity we think we understand but do not respect nearly enough. See, here's the decision that set all of this in motion. And NASA had a schedule. The landing site they picked on the moon, a spot in the ocean of storms near where the Surveyor 3 probe had landed 2 years earlier. That site had a narrow launch window. If they did not go that day, they would have to wait another month. And the pressure was enormous. Apollo 11 had landed on the moon just 4 months earlier. The whole program had momentum. The president was there watching. So the weather people looked at the sky and they said, well, there is no lightning. The clouds have rain, sure. There is a cold front. But the launch criteria say no launch if there is lightning in the area, and there is no lightning. Green light, nobody asked the question that mattered. Nobody asked, what if the rocket makes its own lightning? Let me take you inside that capsule. Commander Pete Conrad is in the left seat. Dick Gordon is in the middle. Alan Bean, the lunar module pilot, is on the right. The 5 enormous F-1 engines at the bottom of the Saturn V have already lit. 7.5 million pounds of thrust is pushing them off the ground. The noise is unimaginable. The vibration shakes your teeth. For the first 36 seconds, everything is exactly as it should be. Then the whole world turns white. A bolt of lightning hits the rocket. Not from a thunderstorm. There is no thunderstorm in the usual sense. The rocket created its own lightning. And that, right there, is the physics lesson hiding inside this story. But I will get to that. First, I want you to feel what happened next. Gordon in the middle seat says the first thing any honest person would say. He says, "What the hell was that?" Conrad looks at his instrument panel, and it is chaos. Every warning light on the board is lit. He later said it looked like a Christmas tree. Voltage readings are jumping around. The fuel cells, all 3 of them, have disconnected. The spacecraft is now running on batteries alone. The batteries were never designed to power the whole ship for more than a short time. If nothing changes in the next few minutes, the mission is over. Maybe worse than over. And they do not even know what happened. Nobody told them they got hit by lightning. From inside the capsule, you cannot see outside very well during launch. Conrad maybe saw a flash. But the instruments are not telling him anything useful because the instruments themselves are broken. That is the part I want you to really sit with. The instruments are supposed to tell you what is wrong. But what do you do when the thing that is wrong is the instruments? Down in Houston at Mission Control, the screens are showing garbage. Not zeros, not error messages, garbage, random numbers, telemetry that makes no sense at all. Flight Director Jerry Griffin is looking at this, and he is thinking, I am going to have to call an abort. We are 36 seconds into this flight, and I am going to have to tell these 3 men to come home. 16 seconds later, before anyone has figured out the first problem, a second bolt of lightning hits. This one knocks out the inertial guidance system, the platform that tells the spacecraft which way is up, which direction it is moving, how fast it is rotating. Gone. The navigation ball in front of Conrad is spinning aimlessly, like a toy. They are riding a rocket, traveling faster than the speed of sound, accelerating hard, and they do not know their own attitude. They do not know where they are pointed. Now, here is the remarkable thing. The Saturn V rocket itself, the launch vehicle underneath them, had its own separate guidance computer. And that computer was fine. The lightning hit the spacecraft, the capsule on top, but the rocket's own brain was untouched. The Saturn V's instrument unit, the ring of electronics that sat between the 3rd stage and the spacecraft, had its own power supply and its own inertial platform. It kept tracking their position, their velocity, their attitude. It kept sending commands to the engines. So the rocket kept flying a perfect trajectory, straight and true, even while the 3 men sitting on top of it were staring at a dead instrument panel and wondering if they were about to die. There is another detail here worth mentioning. The guidance computer inside the command module, the one that was disrupted by the lightning, used something called core rope memory. The programs were literally woven into tiny magnetic cores by hand, ones and zeros encoded as threads passing through or around ferrite rings. This memory was read-only. You could not erase it. You could not corrupt it. A voltage spike could scramble the computer's temporary working memory, sure. It could confuse the current calculations. But the program itself, the instructions telling the computer how to navigate, how to compute trajectories, how to fire engines, all of that was physically woven into wire and could survive anything short of physical destruction. So once power was restored and the platform was realigned, the computer could pick right up where it left off because its brain was made of wire that lightning could not rewrite. The rocket did not care about the lightning. It just kept going. Dad, there is something both comforting and terrifying about that. All right, so what actually happened with the electricity? Let me explain the physics because it is beautiful in a terrible sort of way. You have got a Saturn V rocket. It is 363 feet tall. It is made of metal. And trailing behind it from the moment those engines light is an enormous plume of exhaust gas. That exhaust is not just hot air. It is ionized gas. It is full of charged particles, free electrons, ions knocked loose from their atoms by the incredible temperatures in those engine bells. The flame coming out of the bottom of a Saturn V is a column of electrically conductive plasma. So picture this. You have a tall metal object connected to a long column of conducting gas, and that column stretches all the way back down to the launch pad, which is connected to the ground. The whole assembly, rocket plus exhaust plume, is about 1.2 miles long. You have just built the world's tallest lightning rod, and you are flying it straight up into a cloud layer that is carrying an electric charge. Now, here is the thing about lightning that most people get backwards. People think lightning needs a thunderstorm. Big dramatic cumulonimbus clouds, thunder, the whole show. That is certainly one way to get lightning. But what lightning actually needs is an electric field strong enough to break down the air and create a conductive channel. Normally the atmosphere is a pretty good insulator. Air does not want to conduct electricity. The molecules are electrically neutral, just bouncing around, minding their own business. But if the electric field gets strong enough, roughly 3 million volts per meter in dry air at sea level, things change. Electrons get ripped off molecules. Those free electrons accelerate in the field, slam into other molecules, knock more electrons loose, and you get an avalanche, a cascading breakdown, a channel of ionized gas that can carry enormous current. That is what a lightning bolt is, a sudden, violent electrical breakdown of air that was moments ago a perfectly good insulator. The cold front sitting over Cape Kennedy that morning had clouds with electric charge in them. Charge separation happens in clouds all the time. Ice crystals and water droplets collide, exchange charge, and the heavier particles carry negative charge downward while the lighter ones carry positive charge upward. You end up with an electric field between the top and bottom of the cloud and between the cloud and the ground. But on that particular morning, the field was not strong enough to produce natural lightning on its own. The electric field was below the breakdown threshold. No natural lightning was occurring anywhere nearby. And that is exactly why nobody thought there was a problem. The launch rules at the time said do not launch if there is lightning in the area. Well, there was no lightning, so they launched. But they forgot something, or rather they had never considered something. The threshold for triggered lightning is much lower than the threshold for natural lightning. Much lower. If you stick a tall, pointed, electrically conductive object into a weakly charged electric field, you change the geometry of that field. You concentrate it. The charges in the conductor rearrange themselves, piling up at the ends, especially the top. The electric field at the tip of the object can be many times stronger than the background field. It is like taking a gentle slope and turning it into a cliff. The rocket and its exhaust plume amplified the local electric field until it was strong enough to initiate a discharge that never would have happened otherwise. The rocket did not get struck by lightning. The rocket caused the lightning. This is a fundamental principle. In physics, we talk about conductors and electric fields. Put a long conductor in even a modest external field, and the charges in the conductor rearrange themselves. They pile up at the ends. The field at the tips gets much stronger than the background field. This is why lightning rods work, by the way. You put a pointed metal rod on top of your building, and it concentrates the field at its tip, which encourages the lightning to strike there instead of somewhere else. The Saturn V did the same thing, except nobody planned for it, and nobody wanted it. The first strike at 36.5 seconds was a cloud-to-ground discharge. The bolt came down through the rocket, traveled along the exhaust plume, and hit the launch pad. Cameras on the ground captured it. You can see the bright channel running from the cloud through the rocket's position, all the way down the trail of exhaust back to the ground. The second strike at 52 seconds was a cloud-to-cloud discharge. It did not go to ground, but it still passed through the vehicle. The electrical surge from these strikes created a voltage transient inside the spacecraft. Now you might ask, why did the lightning affect the electronics at all? Is the spacecraft not a metal shell? Should it not act like a Faraday cage and keep the electricity on the outside? And yes, partly it does. A Faraday cage works by allowing charge to redistribute on the outer surface of a conductor so that the electric field inside is zero. If you sit inside a metal box and lightning hits it, the current flows on the outside and you are safe, in principle. But the Apollo spacecraft was not a sealed metal box. It had antennas poking out. It had wires running from internal systems to external sensors. It had umbilical connections between the command module and the service module. Every one of those penetrations is a pathway for a voltage pulse to sneak inside. The current does not need to punch through the hull. It just needs to find a wire, any wire, that bridges the gap between outside and inside. And that is what happened. The lightning current found paths into the spacecraft's electrical buses through external connections. It induced voltages on internal wiring through electromagnetic coupling. Think of it this way. You have delicate electronic instruments designed to operate within very precise voltage ranges, maybe 28 volts on the main bus, tightly regulated. Suddenly a pulse of current floods through the system. Power buses spike, then drop. The fuel cells, which are essentially chemical batteries that generate electricity by combining hydrogen and oxygen, have protective circuits. Those circuits detected the abnormal voltage and did exactly what they were designed to do. They disconnected. The fuel cells said, something is very wrong and I am shutting down to protect myself. From the spacecraft's point of view, this was the correct response. The fuel cells protected themselves, but from the crew's point of view, they just lost their main power supply. The backup batteries kicked in, but batteries alone could not sustain the spacecraft for long. And then there was the signal conditioning equipment, the SCE. This is the piece of hardware that most people have never heard of, but that saved the entire mission. The SCE takes raw sensor data from all over the spacecraft, voltages, temperatures, pressures, and converts it into a format that can be transmitted as telemetry back to mission control. When the lightning hit, the voltage drop affected the SCE's power supply. The SCE shut itself down because it detected an undervoltage condition. Without the SCE, mission control screens turned to gibberish. They could not read any of the spacecraft's vital signs. So here is the picture. 3 astronauts with a dead instrument panel. Mission control with screens full of nonsense. The rocket still climbing perfectly, but nobody able to confirm that the spacecraft itself is safe. Griffin, the flight director, is about to call an abort. And then a 24-year-old engineer named John Aaron does something extraordinary. Aaron was the electrical, environmental, and communications officer known as the ECOM. His job was to monitor the spacecraft's electrical systems. He was a kid from rural Oklahoma, grew up on a cattle ranch, went to college to study physics, and ended up at NASA almost by accident because a friend suggested he apply. He was quiet, he was meticulous, and he had a habit that his colleagues noticed. He was endlessly curious about things that did not seem to matter. If something looked odd during a test, even something minor, he would go track it down. Not because anyone told him to, just because it bothered him not to understand it. About a year before this launch, Aaron had been observing a test at Kennedy Space Center, and the telemetry had gone crazy in almost exactly the same way he was seeing now. The numbers on the screen turned to nonsense. Random, garbled data that looked like the system was hallucinating. Most people in the room shrugged. The test moved on. The anomaly was minor, a power glitch. But Aaron could not let it go. He went and talked to the engineers from North American Aerospace, the company that built the command module. He found that the problem was related to the signal conditioning equipment, and that when the SCE lost voltage in a certain way, its output became exactly this kind of garbage. Not zeros, not blank screens, a specific pattern of meaningless data. And he learned that switching the SCE to its auxiliary power setting fixed it, because the auxiliary mode bypassed the undervoltage protection and let the equipment run on whatever power was available. So Aaron says to the flight director 4 words that have become legendary. He says, "Flight, try SCA to auxiliary." Griffin has no idea what he is talking about. The Capcom Gerald Carr has no idea what he is talking about. Carr says, "What the hell is that?" and he relays the instruction to the crew anyway. Up in the spacecraft, Conrad is equally confused. SCE to auxiliary? Where is that switch? But Alan Bean knows. Bean, who had studied the command module's electrical systems inside and out, who had joined this crew as a late replacement, and had thrown himself into learning every obscure switch and circuit, reaches down to panel 3 and flips a small 3-position toggle switch from normal to auxiliary. The telemetry comes back. Just like that. Mission control screens light up with real data again. Aaron looks at the numbers and confirms the spacecraft is basically intact. The fuel cells are offline but can be restarted. The guidance platform is tumbled but can be realigned. The Saturn V is still flying true. Griffin makes one of the gutsiest calls in the history of the space program. He says, "We are continuing. Within about 10 minutes, the fuel cells are back online. The guidance platform is realigned using a star sighting. The spacecraft systems check out, and Apollo 12 goes to the moon. They land within walking distance of the Surveyor 3 probe, which had been sitting on the lunar surface since 1967. They bring pieces of it home. The mission is a complete success, but it very nearly was not. Now here's what I want you to take away from this. Several things. First, the physics have triggered lightning. Before Apollo 12, nobody at NASA had seriously considered the possibility that a rocket could create its own lightning. They worried about launching into existing thunderstorms, sure, but the idea that the vehicle itself, by virtue of being a tall conductor trailing an ionized exhaust plume, could trigger a discharge in a cloud that was not producing lightning on its own, that idea was not on the radar. After this mission, they studied it intensely. They brought in atmospheric physicists, electrical engineers, people who spent their careers studying lightning, and they developed new launch rules. Do not launch through certain types of cloud formations above a certain altitude. Do not launch when the electric field exceeds certain values, even if no natural lightning is present. These rules are still in effect today. Every rocket launch, the weather team evaluates not just whether there are thunderstorms, but whether the conditions could allow the vehicle to trigger its own lightning. Second, the vulnerability of instruments. I think about this a lot, actually. We build machines to tell us about the world. Thermometers, voltmeters, gyroscopes, accelerometers. And we trust them. We have to trust them, because once you are inside a rocket climbing through the atmosphere, you cannot stick your head out the window and look around. You are completely dependent on what the instruments tell you. But the instruments are physical objects. They run on electricity. They have power supplies and circuits and components that can be disrupted by exactly the same phenomena they are trying to measure. A lightning strike is an electrical event, and the instruments that monitor the spacecraft's electrical systems are themselves electrical systems. The thing you need most is the thing that fails first. This is a deep problem. It shows up everywhere in physics and engineering. You try to observe a system, and the act of observation is itself part of the system. Your measuring device is not separate from the thing being measured. In quantum mechanics, we talk about this all the time. The observer affects the observed, but it happens at the macroscopic level too. Your voltmeter draws current, your thermometer exchanges heat, and your spacecraft telemetry system can be knocked out by the very electrical event you most desperately need it to report on. Third, and this is maybe the most important, redundancy and the limits of design. The Apollo spacecraft was extraordinarily well engineered. Multiple backup systems, redundant power supplies. The SCE itself had 2 internal power supplies for redundancy, but both power supplies were fed from the same flight bus, which meant that when the voltage on that bus dropped, both supplies were affected simultaneously. The redundancy did not help because the failure mode was one that affected all the redundant paths at once. This is what engineers call a common mode failure. You can have 10 backup systems, but if they all depend on the same power source, or the same physical wire, or the same assumption about the environment, then a single event can take them all out together. The auxiliary setting on the SCE bypassed the undervoltage protection circuit. It let the equipment run even when the voltage was below the normal threshold. It was essentially an override. And the only reason anyone knew to use it was because one young engineer a year earlier had gotten curious about a weird test result that everyone else had ignored. That is the lesson that haunts me. The system worked, but barely. Not because of brilliant design, because one person paid attention to something strange and remembered it at exactly the right moment. If John Aaron had not been watching that test, or if he had shrugged it off the way everyone else did, the call would not have been made. The SCE would have stayed on normal. The telemetry would have stayed garbled. And Griffin would have called an abort, ending the mission 36 seconds after launch. Or worse, if the abort itself had complications. 3 men might not have come home. Physics does not care about your schedule. Physics does not care that the president is watching, or that you have already landed on the moon once and you want to do it again. An electric field in the atmosphere follows the laws of electrostatics with perfect indifference to human ambition. A voltage transient propagates through a circuit at very close to the speed of light, obeying Maxwell's equations without the slightest concern for whether you wanted it to happen or not. And that is the warning I take from Apollo 12. We are clever enough to build rockets that can carry people to the moon. We are clever enough to invent instruments that can navigate through space with extraordinary precision. But we are not always clever enough to anticipate every way that nature can interfere. The atmosphere had a small electric charge in it that day, not enough to make lightning by itself, and we flew a giant metal lightning rod straight through it. After Apollo 12, NASA imposed strict weather launch criteria that included conditions for triggered lightning. They brought in experts on atmospheric electricity. They required real-time monitoring of electric fields at the launch site. And they added a rule that seems so obvious in hindsight it is almost embarrassing that it needed to be stated. Do not launch a rocket into clouds that might be carrying electric charge, even if those clouds are not producing natural lightning. And you might think, well, lesson learned, problem solved. But nearly 2 decades later, in 1987, an Atlas Centaur rocket carrying a communications satellite was struck by triggered lightning during launch and had to be destroyed. The vehicle and its payload were lost entirely. The phenomenon that Apollo 12 survived killed a different rocket. So even with the rules, even with the knowledge, the danger persists if people are not vigilant. But here is the really sobering thought. The parachute system that would bring the command module back to Earth at the end of the mission used explosive bolts. Small pyrotechnic charges that, when fired, would release the parachute cover and deploy the chutes. These charges were wired into the spacecraft's electrical system. If the lightning had triggered those charges prematurely, the parachute mechanism would have been destroyed. And 10 days later, when the command module came screaming back into Earth's atmosphere at 25,000 miles per hour and needed those parachutes to slow down, they would not have worked. The capsule would have slammed into the Pacific Ocean and all 3 men would have been killed. NASA knew about this possibility. They spent the entire 10-day mission quietly worrying about it. They did not tell the crew. The parachutes worked fine. But nobody knew for certain that they would until they actually deployed. That is the kind of thing that keeps engineers awake at night. A failure mode that you cannot test, cannot verify, and cannot fix in flight. You just have to wait and hope that the physics was on your side. I love this story because it has everything. It has the raw power of nature, a lightning bolt triggered by human technology. It has the fragility of our instruments, systems designed to be robust brought to their knees by an event nobody predicted. It has human brilliance, a young engineer remembering an obscure anomaly and speaking up at the critical moment. And it has the cold, beautiful indifference of physics, the Saturn V flying perfectly, while the humans on top of it were lost in an electrical storm of their own making. Nature does not read our checklists. It does not care about our launch windows or our backup plans. It plays by its own rules. And those rules are the laws of physics, and they apply every time, everywhere, without exception. Our job, as people who want to understand and work with nature, is to learn those rules so well that we are never surprised, but the truth is we are sometimes surprised. And when we are, the best we can hope for is that someone in the room has been paying attention. So here is what I want to leave you with. Think about your own instruments, not spacecraft instruments. Whatever tools you use to understand the world around you, your eyes, your ears, your measuring devices, your models, your assumptions, every single one of them has limits. Every single one of them can be blinded by the very thing you most need to see. The question is not whether your instruments will ever fail you. They will. The question is whether you have thought carefully enough about how they might fail, and whether you have someone like John Aaron on your team who has been curious enough to study the weird, unexplained, supposedly minor anomaly that everyone else dismissed. That is the real warning from Apollo 12, not just about rockets and lightning, about everything. What instrument in your own life are you trusting without questioning how it might fail?